Hello, world. Welcome to MegoxCast. I am your host, John, joined by,
Kyle.
for this episode. Today, we will talk about the history of computing. Now, Kyle, talk a little bit about yourself.
I'm 19. I'm a freshman in college, and I'm majoring in computer science. So I hope I have enough information without sounding stupid.
Do you think you'll sound stupid?
Hopefully not.
That
Probably
would-
to someone that knows more than me.
Yeah, but I mean, who watches this podcast and knows more about computers?
I don't know. Get
Good
like
point.
what, 100 views per episode?
Oh, yeah.
150 sometimes. Honestly,
So,
that exceeds. Honestly, that kind of exceeded my expectations. But yeah, good job, man. Good job.
yes, you heard that here first, folks. Good job. Anyway, we will start with the first topic, ancient times. So, Kyle, like, I can't even imagine computers being around during before the 20th century, you know? Those computers in SpongeBob, that's what I thought the first computer was, not all this like bleep blorp stuff that we see, that are like huge, big, giant machines, you know what I'm saying?
Yeah, well, I mean, they weren't around in ancient times. They didn't even have the concept of computers in ancient times. But um, the ideas for computing and the ideas for the math behind it and stuff really started in ancient times, before any of it was realized. But
Dang.
I mean, the first um, the earliest known calculating device was the abacus, and this is a device that dates back thousands of years. And the exact
Older than me?
date of Oh yeah, and the exact date of its invention is it's difficult to pinpoint because it was developed in different ancient cultures around different times. So the Sumerians, and the ancient Mesopotamians had their own version of it. 3,000 years, actually, like almost 5,000 years ago.
Oh my gosh.
China too. Um, well, I guess the earliest version of it was really like almost 5,000 years ago, so like 4,300 years ago. So yeah, that's pretty old.
Yeah, it is old.
Um,
Jeez.
yeah, and abacus. I've never really used an abacus, so I think they're just
I
for
remember
helping
using it
you.
like when I was a baby or something, like trying to be like, look, mommy, I'm smart, you know?
Aren't they for like helping you do multiplication?
Okay, you know what? I was I used this thing called a calculator, but I'm assuming it was like an earlier form of a calculator, or at least like a something to keep track of like certain numbers, like if you had a certain amount of like cattle or something,
Oh yeah,
right?
maybe. Yeah, I should have probably looked into more. I should have looked into how abacuses worked and whatnot, because I honestly don't know. So
Well, I mean,
that's
I
where my
from
knowledge
my
ends on that.
knowledge, yeah, from my knowledge, it's like the bottom, for an example, was like one increments of one. The second one was 10, then 100, then 1,000, and then they just
Yeah,
did it
well,
like that.
I think these ancient cultures didn't use base 10 number system, so it was probably different than tens, hundreds, thousands. But
Yeah, they probably used maybe fives.
yeah, maybe. I don't know. I mean,
We don't know,
Indians
but
had like base 4, I know.
yeah,
But base 10's, the most based one because we have
base
10 fingers. Yeah,
exactly.
10 finger. Yeah.
Yeah, 10 fingers to finger. Anyway,
All right.
so
Yeah.
after the abacus, what would you say was like cray cray, you know, like, oh my gosh.
Um well, I mean, it doesn't necessarily work like that because you know, different things happen concurrently and whatnot. So the next thing I had notes on were algorithms. So an algorithm is basically just a step-by-step procedure designed to perform a specific task or solve a particular problem. So they could be as simple as a recipe for a meal.
Oh
So
my.
it's like, yeah, so just crack some eggs, put some water, put some dough, and you got cake.
I
And
like me some cake.
yeah, and they're, at their most complex form, they could be like large language models, for to run ChatGPT. That I would say is probably one of the most complicated algorithms. And so I'm just going to be focusing on mathematical algorithms because non-mathematical algorithms like recipes I don't really consider important to the history of computing. But algorithms are essentially just step-by-step instructions, and humans have really been using them since the dawn of civilization, since we could write stuff down. So one of the earliest known algorithms, mathematical algorithms, is often attributed to the ancient Mesopotamians around 4,000 years ago. And so the algorithms they made were for multiplication and division. So like, long division. That is an example of a mathematical algorithm that they probably invented. And multiplication too, because when you're doing like 5 times 3, the algorithm would be to add 5 to itself 3 times. So
Yeah,
yeah,
because then
and
it goes into it 3 times. Yeah.
yeah, and so those are examples of probably the earliest known mathematical algorithms. And then so another famous ancient mathematical algorithm is Euclid's algorithm, developed by the Greek mathematician Euclid 2,300 years ago. And Euclid's algorithm is used for finding the common divisor GCD of two numbers. This algorithm is used a lot in cryptography, for example. I can't really think of any other example off the top of my head, but it is used a lot. And so it involves just a series of step-by-step instructions for repeatedly subtracting the smaller number from the larger number until the two numbers are equal, at which point the common divisor is found. And what's interesting about Euclid's algorithm is it's the first algorithm to be mathematically proven to work in every single case. So what that means is, given any input, an infinite amount of numbers inputted into the algorithm, it'll work no matter what. And so Euclid proved that in an infinite amount of cases it will work. Now he didn't do it by putting in an infinite amount of numbers to make it work. I mean that would be impossible. So what he did is he provided a formal proof to do that. And I won't be going into how the proof works, but basically it uses logical deduction to figure it out. And so
All right.
yeah, and so proving algorithms is pretty important because you want to be sure that your algorithm works. Will always work, but it's not always needed. So like some algorithms have a finite amount of possible inputs, so you won't always need to do that. So algorithms with a finite amount of possible inputs only really need to be proven by plugging and chugging all the different amount of possibilities. All right, let's move on to propositional logic. So in digital computing, propositional logic is used in things like digital circuit design, algorithm design, and logic flow in programs. And the origins of propositional logic can be traced back to the ancient Greek philosophers, particularly Aristotle. So that was like 2,300 years ago. And Aristotle introduced many concepts related to logic, including the study of statements, their truth values, of logical operators. So yeah, this was stuff used a lot in philosophy at the time. Which was really interesting. You got anything to add so far?
No, I mean this propositional logic thing. What is the difference you'd say between that and algorithms? Because I'm still a little confused about that.
Um, Propositional logic really just deals with logic. Um, you didn't you learn about some basic propositional logic in one of your classes?
I think a little bit, yeah. I think it was maybe the intro to math. It was the, you know, where it said it like one truth and then a lie, something like that. Or if it said like no, it had like two negatives and it made a positive, that kind of thing.
So like
Said
you
like
proved
I
that a
am,
negative.
yeah.
Okay, did you do any like proofs with propositional logic?
From what I remember, I don't remember too much about the proofs.
Okay.
So
Yeah, so I mean, in terms of other fields of philosophy, I don't really know exactly what propositional logic be used for. I just know like it's really the basis of math. And so propositional logic is used to prove math works. Um
that's
so yeah, it's
good.
pretty important. So yeah, I mean really philosophy really spawned everything. I mean it spawned math, it spawned science. It spawned base any field of study is spawned from philosophy.
Yeah,
So
and people don't really look too highly on philosophy majors.
yeah, they really don't. Um I don't know how it's taught in school. But I think it is pretty important. I think it is pretty underrated, honestly, considering how important it's been.
Yeah, but I think just in these modern times, people don't want to think too much, so philosophy is just not in their wheelhouse.
Yeah.
So, how it is. Anything else about propositional logic you wanted to talk about?
In this era, not really. So, I mean, the last thing I have for this era is the Caesar cipher. This is the first ever cipher. Do you know anything about ciphers?
I know about Bill Cipher from Gravity Falls.
Oh, I haven't watched that show.
You
But
should. Good show.
watched some of it, but yeah, I stopped.
I mean, all
Anyways,
I know about
um,
ciphers is it's kind of like a code or like some like maybe a a hidden like encoded message or something like
yeah,
that.
exactly. They're used for encryption, and so you need encryption to keep secrets. Um, so like
Like
when you're
Morse
sending
code.
a message, no, not really. Well,
Oh, okay.
no, not really. No. So like when you're sending a message across the internet, the message gets put into the cipher. The cipher scrambles that information, sends it to the other computer which you're trying to send that message to, and then the other computer decrypts that message and then read it. And this is so like, while it's being sent across, someone in the middle can't pick up that message and read what you're trying to send. All right. And so let me talk about Caesar cipher. It is named after Julius Caesar, the Roman military general from that time. Wasn't he like the emperor?
Yeah, there was like an entire play about him. I think it was like Shakespeare, Julius Caesar. He got stabbed like 20 times by
Seems
Brutus
like
or
a bad.
whatever, and then he was
Yeah, he seems
bad.
like
He
a
was
badass.
badass.
Yeah, like he was a military general, a fucking emperor. Pretty sure he's a
He made some
statesman
pretty good
too.
pizza
He was a Yeah, he was a mathematician too. I mean, he had the bronze and the brains.
and the
You know.
pizza.
Yeah. I don't know if he was much of a mathematician, but he did make the first ever cipher, so good on him. Anyways, so yeah, and he invented the cipher so that while um he was sending messages during his military campaigns, like he would write a letter to his troops, so while like to tell them what to do or whatever. And so while that letter's being sent, if it's intercepted by the enemy, they can't read what they're trying to say. And so Caesar cipher operates by shifting each letter in a message of positions up or down the alphabet. So So let's say you have the word hello in your message, right?
Yeah.
So let's say we agree on a key to decipher this message. So what I'm going to do, I'm going to take H, the first letter in this message, and I'm going to shift it 3 letters down the alphabet. So A, B, C, D, F, G, H, I, J, K. So H becomes K, right? And we do that for the rest of the letters in the message.
Oh yeah, that happened in Gravity Falls. They used to do that like 3 letters back or something. That was and they put in some like uh sentences and all of them were under this code or he had to put 3 letters back. So I'm guessing like H would be uh I think it would be like E or something.
Yeah,
You know what I'm
maybe.
saying?
I might have
No.
I might have done it wrong in my head, but yeah,
Okay, no, it's
basically
all good.
H is so all the letters in the original message are shifted up 3 letters,
Mhm.
and then once and then once you get the message, since we both agreed on the same key to encrypt the message, you're gonna shift it backwards 3 letters, each of the letters that are now shifted up 3 letters, and so when you shift them back 3 letters, you get the original message.
Well, that's
So that's
good. I
how
don't
it
want
works.
to I don't want to read the encrypted one cuz I'll be like, "What are you talking about, Kyle?"
Yeah. Okay.
So,
It's
yeah.
and so let's say you do have an encrypted message in Caesar cipher. Let's say you intercept a message in Caesar cipher. Can you think of a way, without knowing the key, that you could break this encryption?
Without knowing the key. Oh, that's a toughie, Kyle. Uh oh my. I
There's
feel
a
like I'm
way.
on. Oh, what's
There
up?
is a way, and there is a way, and this is
What's the
why
way?
it's not. Think about it. If you have this message and you know it's encrypted in Caesar cipher, and there's only 25 letters in the alphabet, or is it 26? Anyways, so you
Hmm.
know there's 25 letters in the alphabet. All you have to do is try all you have to do is try 1 through 25, different possible shift backwards, and once you get a readable message, then you've broken the cipher.
I mean,
That
yeah,
makes
that's
sense?
the logical way of doing it, but at the same time, it would take a while.
I mean, it only take 25 times, and if you have a computer do it for you, it would take less than a second.
Wow.
So, yeah, and this is why the cipher is not used anymore, because once it was figured out how to break the cipher, it was useless.
It was probably
So,
figured out in the first time they figured out how to read the cipher. You know what I'm saying? So if they found out there was 3 letters back, they were like, "Oh, I mean, if the concept is that it's just going to be a number of letters back, then yeah, they would probably have to do one where it's like every other thing to make it even more complicated, right? So some of them would be like this amount, this would just be the regular letter. So then it would complicate people that are thinking, "Hey, all the letters are encrypted." But if you have half of them, they're going to be confused. I
yeah,
don't
I
know.
mean,
That was just the
there's
yeah.
I mean, yeah, I mean that's a good line of thinking because there are many different types of ciphers that were invented to try trick, trick the interceptors to not being able to read the messages.
Yeah,
And
what did
over the years,
why did Julius Caesar want to make a cipher? That's a good question.
I already answered that. It's
Oh,
because he
yeah,
was a
say it again.
military general and he was writing letters to, his troops and stuff.
Oh,
And
okay, I
so he
got you.
didn't want them to be intercepted. Yeah. And so yeah, there's been many different types of ciphers invented throughout the years. All of them have been broken.
Dang.
Um, all of them. There's always been a way, eventually, where some mathematician will figure out how to break these ciphers. Except for the cipher we use today, which is SHA-264, and this algorithm is used for every encryption. So everything, your bank statements, your passwords,
Yeah, I
it's
wouldn't
all
want that
done
to
in
be, you know.
SHA-264. And so if someone were to figure out how to break SHA-264, you know, they'd be able to flip over the entire world essentially if they wanted to. So yeah, that's
No,
that.
I got you. Um, all right. Anything after this Caesar cipher that you would say is important
Um,
for uh
that's all I have
oh, that's
for
all you have
ancient times.
for ancient times. What okay, so you want to go to the next topic?
Yeah, so
All
before the
right. So
20th
before
century.
the yeah, one second. Before the 1900s. So, yeah, I mean, yeah, like I just said, Kyle, I don't even know the kind of stuff that happened before the 1900s when it came to computers because I knew computers helped make the astronauts go into space, but I can't even imagine them using it before that. You know what I'm saying? Before even the modern and before even cameras or photography.
Yeah,
So
and there is, you know, and I will be talking about some really interesting quote unquote computers throughout the before the turn of the 20th century. Um,
all right, let's
yeah,
do this.
and this is before electricity. So, the first automated calculator is the Pascaline calculator. So this is the earliest mechanical calculator. It was invented by Basil Pascal in 1642 when he was just 19 years old. And so he was a child prodigy. He was a mathematician. And so he designed this to help his father, a tax collector, perform arithmetic calculations more quickly and accurately. Because everything had to be done by hand at that time, and that was probably annoying. And so the Pascaline calculator performed only addition and subtraction, and it used a series of gears and wheels, each wheel representing a digit 0 through 9. When a number was added, the corresponding wheels would turn to display the result. Um, and actually, after the invention of the Pascaline calculator, this actually was like the first case of tech scare, because mathematicians at the time
Oh
were like,
my.
"Oh no, it's gonna start replacing us." And so, yeah, I mean, nowadays we have the AI scare, but really the tech scare started all the way back in 1642. You believe that?
No, I can't. Jeez. Oh, so you're saying that they thought they were already going to lose their jobs and lose their, you know, humanity already? Like the machines were just that good?
I mean, probably just like clerks and stuff, but
Hmm.
yeah, I mean that was really the first time there was a tech scare. And okay, let's move on to Gottfield Leibniz and his contributions to computer science.
All
So
right.
Gottfield Leibniz is considered to
Garfield, ooh.
be, I'm gonna say, or Gottfried. I don't know how to pronounce his name.
Yeah,
Let's
hopefully
just
he
call him.
didn't hate Mondays.
Maybe he did. I don't know. So he's actually considered to be the first computer scientist because of his advancements in binary logic. And so he actually came up with the binary number system, base 2, and devised a theoretical machine that could do binary arithmetic. It wasn't actually ever built, but he designed the blueprints essentially. Okay, so do you know anything about binary number system?
I know it's from my knowledge 0101 and it
Yeah.
can be used to to calculate numbers to I'm pretty sure it can even be used for a code kind of like with Caesar cipher, but like just a little bit different. I feel like it's a very you know useful system of code
Yeah, so
from what I know.
essentially we just have, it's really just a number system. So we have base 10, so we count from 0 to 9, and then once you add one more number, you add another digit, right?
Hmm.
So, and then you add another 9 to 10, and then you add one more number to 19, 20, and then you do that to 99, you add one more number, and you go to 3 decimal places. So in base 2, so you start in base 2, you only have 2 possible ways of representing a digit, 0 and 1. So 0 would just be 0, 1 would just be 1 in the first digit, and then you add another 1, then you go to the next digit. And so 2 in binary would be 1, 0. And then you add another digit, another 1, you get 1, 1, and that will be 3. You add another 1, and you get another digit, and then you have 1, 0, 0, be 4. And you keep doing this. 1, 0, 0, 1, 5, 1, 0, 1, 0, 6. So, and that's how binary into binary sum essentially works. And
Alright.
you can still do all the different arithmetic on it. You could do addition, subtraction, multiplication, division. You could do all of that. So
What can it do? 2 plus 2 equals 4.
do any calculation.
Yeah,
It's
but
just
how would that be represented in a binary?
2 plus 2 equals 4.
Yes.
Just be 1, 0 plus 1, 0.
Equals
1,
1,
0,
0, 1,
0.
0? Oh,
1,
1,
0,
0,
0.
0. So 100 would 1, 0, 0, or what looks like 100, but 1, 0, 0 would be 4.
Yeah.
Dang. Okay, I think I get it now. Jeez.
Yeah, and there's an
Crazy.
infinite amount of number systems. You know, you could have 100. You could have hundreds of different possible symbols for a digit. All right, and
Yeah.
so yeah, binary is one of the most, almost the simplest. Before that, I think the most simplest. I think there could be base 1. So base 1 would be like, you know how in like films and stuff, you see the prisoner and he's like etching the marks in the wall to count the number of days.
Yeah. That would just be
I
in
think.
fives though.
Well, I mean, essentially, base 1, I believe would just be an etch, just be one symbol for each digit. So like if you wanted to represent like 4 in base 1, it'd just be 4 etches. So and if you want to represent 5 in base 1, it'd just be 5 etches.
Yeah, but
So,
it would be 4 and then the fifth one would be uh, you know, diagonal.
yeah, but I was just using that as
As
a
an example, yeah, no. That's a good point. I was just yeah. I mean, that makes
like
sense.
before um I think that was like the most simple number system that was ever invented. Like the ancient, our like ancestors when they're counting the cattle like 10,000 years ago, they just etched some marks on a log or something.
Yeah, and then they invented the abacus and they were like, "Hey, yo, pause. I can move a bead? Oh, yeah."
Yeah, and I think before the abacus, they invented a more complex number system after that to like have more symbols in a digit. And really, just the more digits you have, or the more symbols for a digit you have, the more compact you could represent a number in a smaller space. Probably when like writing came around, when they first had writing and they had limited space to write, they were like, "Oh man, we gotta compact these numbers down more." So that was probably the reason for that.
All right. So,
And
talked about binary. Oh, what's up? Are you have more stuff to talk about binary?
um, I guess we could move on from that. All right, and then Leibniz's calculating machine. So he
Ooh.
actually extended on the Pascaline calculator. It was still mechanical, but his machine could now do multiplication and division. So yeah, so step up. That's all I have on that. All right,
Oh, okay.
now extension of propositional logic. We talked about how propositional logic was invented in ancient times, used by philosophers, and then some guy named George Boole came around in like the 1800s, and he extended on that. So in George Boole's book, the mathematical analysis of logic. He introduced algebraic methods for representing and manipulating logical statements, which later became known as Boolean algebra. And Boolean algebra is a crucial component of modern-day propositional logic for designing circuits. So an example for that would be, we haven't even gotten there yet, though. Should I talk about
You
logic
can
gates?
still talk about it. Yeah, I'd say so.
Actually, yeah, I think I could talk about logic gates.
Yeah, because you're going to talk about
So,
it later too, so it could be like an introduction, and then you'll be like, "Remember this?"
yeah, so I think logic gates. No. Oh, okay. So, hmm.
Kyle,
I
just
mean,
do it. They must
all a
know
logic
about the
gate
logic
really
gate.
is all how a logic gate works is really just an extension of like the symbols in propositional logic. I probably should have talked about it earlier in ancient times, but I'm just gonna talk about. Yeah, I'm just gonna talk about it. So, an OR gate is um for the inputs of these logic gates. There's only two inputs. They're really simple, and so the only inputs are either a true or a false. And so if you have an OR gate, example, and you had two inputs, A and A and B can only be true or false. What the OR gate's going to do is it's going to say A or B. So if A is 0, B is 0, OR gate is going to output a 0. If A is 1 and B is 1 and B is 0, the OR gate is going to output a 1 because because the OR gate is going to output a true if either if either A is true or B is true. So if B is true and A is false, it's going to output a 1 still. And if they're both true, it's going to output a 1 still. It's only going to output false if both A and B are false. So that's the OR gate. And then there's the AND gate. And the AND gate outputs true if A and B are true. Kind of the opposite of the OR gate. And then there's the NOT gate. And the NOT gate inverts one input. So if the input is true, it's going to be inverted in the NOT gate, and it's going to output false. If the input is false, it's going to be inverted, and it's going to output a true. So those are the three logic gates, and there's only three. With Boolean algebra, you could with the mathematics of Boolean algebra, you could prove that all logic gates in a circuit only need to use one type of logic gate, and that's the NAND logic gate. And so all a NAND logic gate is it's a AND gate and a NOT gate at the end. So a NAND gate takes A and B and then inverts it afterwards. And so with Boolean algebra, you could take a circuit that does addition, for example, and this circuit at its most basic component is using AND or NOT gates, right? That's all it's using. Mm-hmm. But with Boolean algebra, you could prove that you only need NAND gates. So essentially, you don't need OR gates. And the reason why I'm talking about you only needing NAND gates is because all computers, all of the logic gates in computers are just NAND gates, and the reason for that is because they're cheaper to mass produce. So that was
always got to be doing the cheaper option, America. Jeez, we can't just do the more what would be the more efficient way, Kyle? Or you think this would be a more efficient way to do?
Actually, I've converted logic gates into just NAND gates, and I think NAND gates usually are more bigger. And so if they're bigger, it's going to take more time So I think actually just using and or not gates might be more fast. Maybe. I'm not exactly sure.
You don't know till you
I
try.
mean, obviously they use them, so I know they're cheaper. So, I mean,
Yeah, but cheaper is
Anyway.
not always better, Kyle. Would you rather
That
eat
is
Fruit
true.
Loops or would you rather eat, colorful hoops? You know what I'm saying?
Yeah, I mean, true, but I can't really I don't know if any computer really even uses all of the logic gates. I think it's just NAND. So even like supercomputers. But maybe it is better all around. I don't know. I don't know, John.
We demand answers, America.
Yeah.
Anyway, no,
Right,
I
let's move
I
on
get you.
to the
Yeah.
let's move on to the most interesting part of this
Oh yeah.
section. The Babbage machine.
Oh yes, the with Anna, Ooh.
Yeah. So the
Yeah.
Babbage
Okay.
machine.
Before we even go, you got to talk about Anna.
Well, I'm gonna talk about her.
Okay. Good. All right.
So
I'm
the
getting
Babbage
ready.
machine. Ready, John. Okay. The Babbage machine was a fully mechanical computer that is supposed to be what's known as Turing complete. I'll go into more detail of Turing completeness later, but basically, Turing complete means it could perform any computational task. And so Carl Babbage's motivation to build the analytical engine was rooted in his dissatisfaction with manual calculation and his desire to create a more efficient and versatile machine for performing complex calculations. So he was a mathematician, and he was employed sometimes to calculate logarithmic tables. And so sometimes he'd produce them, send them out to his clients, and they get pissed off because they'd be wrong sometimes. And so he was like, damn this. I wish there was a better way. And so, yeah. So that's his motivation. And let's talk about the architecture. Oh, and by the way, it was never fully built. So, I mean, if it was actually fully built, then it would have been the first ever computer. It would have been completely mechanical. It would have ran off steam, which is honestly very cool. Like, imagine a steampunk computer. It would have been that. But it was never fully
Dang.
built. They didn't have enough funding. People didn't understand it. And, yeah, it never got fully built because he didn't have enough funding. And so, the analytical engine featured several innovative concepts, including a stored program, a central processing unit, and the ability to perform arithmetic, logical, and branching operations. It would have used punch cards to input instructions and data, an idea that later influenced early computers. And so nowadays we have the CPU, we have the RAM, we have all that. But he called it different stuff. I don't remember exactly what it was, but he called it different jargon. And his jargon was like Victorian English stuff, so you could probably imagine what that'd be. All right, let's talk about Ada
Wouldn't it be
Lovelace.
fun?
Ada Lovelace was an English mathematician. She is
Oh,
associated
Ada.
with the
Wait, Anna or Ada?
Ada,
Okay, I said it wrong, guys. Sorry.
and she is associated with the analytical engine because she wrote detailed notes and annotations on Babbage's work. So she saw a publication of Babbage's work at a university or whatever, and she got interested by it. And she actually wrote a theoretical algorithm for calculating Bernoulli numbers on the machine. So she wrote the code for it essentially. So this is why she's considered the first ever computer programmer.
Woman.
Yeah, she never actually, um, I never actually programmed on it because it was never built. But she did come up with the code for it. So that's interesting. She came up with other concepts for it, such as memory addressing and looping. So yeah, it was never built, unfortunately. But if it did, it would have sped up the invention of computers by 100 years. So we would have had more advanced computers by today, probably, if it was built back then. But
Yeah, we would have had
Nope.
iPhones in like the 1980s.
I mean, yeah, but I mean, first, definitely, electricity would have had to be invented first because this would have been a big machine. This would have been like, I don't know how long it would have taken to calculate things, but just to add 1+1, it would probably take a fucking minute. I don't think it would be very practical at all because it would have just been running off gears and pistons, shit. To
Yeah.
move a number from one address to a number in it, it would have to literally fucking move it on like a conveyor belt or something. Yeah, it would have taken forever to run.
Taking a long time. Yeah.
Yeah. Imagine running fucking Grand Theft Auto on that thing.
or that one game, Cyberpunk.
Yeah.
That would have taken a full century, bro.
Yeah, the Victorian gamers, dude, just having their Babbage machines, bro.
Yo, pause. Oh, dude, what would that even be, bro? All right, they would.
Oh, I'm
Okay,
in a
so
game.
VR ran on the Babbage machine. But all right. So, anything else in the 19th century, before the 19th century, that was important?
Did I talk about when I was born? When it was made, it was gonna be made in the 18th century. So yeah, no, that's the end of that.
All right, so you want to go to the next topic? All right. Modern times. This includes the 20th century. Don't blame me on that decision, by the way. Kyle did say that most of these machines, the ones that were made in the 20th century, are kind of like the ones we have today, but they're just faster now. Is that right, Kyle?
Yeah. Yeah, I mean, all the ideas and stuff for computers were really developed in the 1940s. All the architecture for computers was really all complete during the 1940s after World War II. And really, since then, computer architecture, really all that's been happening is it's been getting faster and faster. I mean, sure, there are some nuances for advancements, but I think the core aspect of computers really have been invented in like before the 1950s. All right, so let's start with the first electromagnetical machine. Man, I hope so. And I hope so far everything I said was mostly accurate. I hope some nerd knows much more than I do, and there's probably gonna be someone.
Excuse me.
Yeah. Oh yeah. I hope. I hope that's not gonna happen, but I think it might. Anyways,
I don't know. I do have a lot of cool people listening to my podcast. I don't got a lot of nerds. All right, Urkel, you better get out of here. You know what I'm saying?
Yeah.
All
Be
right.
some hate comments after it's uploaded, like, no,
Hopefully.
actually.
And then they'll.
Yeah.
I mean, no dropping the N-word, guys. I'm just saying.
All right, so yeah, let's start. Let's talk about the first electromagnetic.
I'm excited.
Machine.
What was it?
So in 1980, Herman Haller invented one of the first electromagnetical machines, referred to as a census tabulator.
We're skipping to the 1980s?
No, this is in
1890s.
I said 18. Did I say 1890s? I might have said 1980s.
Yeah,
but yeah,
so
1890.
Okay, good.
So this guy invented a census tabulator for the U.S. An electromagnetical one.
A little bit about this. Can I say something?
Yeah.
Okay, so from my knowledge, they were doing the census for, the United States because they have it every like 10 years, and they try to do it normally, but there's a lot of people that are immigrating here and a lot of stuff like that, and they could
Yeah.
only do like 7. It took them 7 years to do it, So this guy invented this, right? This machine, and all you had, it was like punch cards, like you were saying, and you put it in there, and it reads the punch card. I mean, there's a lot of technical stuff you can go into that. Something with mercury, like what? And then it happened in like 2 years. They were able to do the census, and that was really cool. I think
Um,
it was even IBM that did it, right? That was their first machine.
yeah. That was their first like electromagnetic machine. I'm pretty sure. I wrote in my notes that he founded his own company, which later became IBM. I think IBM actually was around before that. It just like this company merged with IBM. I think that's what actually happened.
Oh, okay,
But
that makes sense.
also another thing with the census. So we also have beyond immigrants, we also have census for tracking like demographics in the United States, right? Every 10 years.
Yeah. Hmm.
Isn't the reason why it was set to every 10 years is because before they actually had to do it by hand?
Yeah, they kind of had to.
Yeah, I mean nowadays, we could do the census, I'm sure, a lot quicker than
Online.
10 years.
Yeah,
And
everyone
so
just does their part.
yeah, I think people complain about it being every 10 years. And I don't think it really has to anymore. So I don't know why. I mean, our politics are pretty broken, but that's another topic for another day.
I mean, it's easier to keep track of stuff nowadays. Back then, it was really hard.
Yeah. But I mean, my point is like, why hasn't it been changed from every 10 years to less?
I think it's just
Mhm.
because of, a lot of the traditions or just conservative
Yeah,
ways
exactly.
that yeah.
Yeah, that's probably it. But I mean, it shouldn't. So yeah, that's pretty much all I have on there. I don't have any technical details on it. I just put like, um, so yeah, you input punch cards, for the census data. So like a hole in the card represents data like, oh, is this person male? I don't know anything else about what the holes in the card would represent, but it could do
Oh,
like,
like if you're married or if you're not married.
yeah, I think so. And so
Yeah.
you input it into the machine, and it could collect 65 at a time and tally up the results. So a lot quicker.
Yeah.
Yeah. All
And
right.
then Henry Ford heard about it, and they were like, you know what? I want them to work 8 hours a day and then use those punch cards. So then I know that they're working those 8 hours, those 40 hours a week, if you will.
Oh yeah. So didn't they use punch cards back then for
I'd assume so. I
clocking it
mean,
out?
that's where the term came from. Have you not heard of
Yeah.
the hit song Footloose? I'm punching my card. You know, 8 hours for what? That's where it came from. Henry Ford was beaten down on Kenny Loggins, and he was like, "Oh, tell me what I got." I don't know what that was all about, but you got it. It's a good song.
Yeah. Yeah. You really sang that really well, John.
Ah, thank you.
Um. Oh
All right,
yeah.
keep
So
going.
I guess yeah, the census tabulator was really used a lot of other stuff too. I mean, yeah, I mean it did become part of IBM, which stands for International Business Machines. So yeah, I mean I'm
What a
sure.
boring name. Why not just call it, you know, computer business place?
Because the concept of a computer wasn't even realized at this point.
Okay, that's a good point. That's a good point.
Yeah, and I think they
That's
also.
actually
I don't think they
yeah.
just had electrical machines. I think they also had like 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 freaking like bread slicers and shit like that. I think it was just like they had like machines in general.
Oh,
So
okay.
I yeah.
Like
So I think
factory stuff.
yeah. So IBM I think makes more sense.
Oh, okay, yeah, I would say so. All right. So, what after the census machine? What did this lead to?
All right. Well, it didn't lead to anything. And it didn't lead to the next section.
Okay, that's
But
fine.
we're gonna dip into a little more theoretical, abstract shit.
All right.
So first thing I want to talk about is the decision problem, and this is a problem in mathematics. So it was originally posed by David Hilbert, and it asks whether there could exist a universal algorithm that, when given any mathematical statement, could determine whether the statement is provable within a formal system. So Alan Turing's concept of the Turing machine played a pivotal role in addressing the decision problem. In his 1936 paper, Turing showed that there are inherent limitations to what could be computed algorithmically. Turing proved that the halting problem, which asks whether a given program will eventually halt or terminate or run forever, is undecidable. In other words, there is no general algorithm to solve the halting problem for all possible programs and inputs. This disproves the decision problem. So, I don't think I fully understand it myself, but so if you were given a machine, right?
Yeah.
Don't worry about how the machine works, and you have two inputs into the machine and two outputs. So the outputs is either yes or no. Yes, meaning that. Okay, let me talk about the inputs first. So, fuck, you know what? I don't think I know enough about it to talk about it.
Fine.
I don't think I to talk about I don't think I know enough about it off the top of my head to talk about how he proved that the decision problem is false. But basically, Alan Turing, with his concept of a Turing machine, disproved that there could exist a way for an algorithm or machine to you know what? I actually don't think I know enough about it. I'm sorry. I think I'm just gonna
That's all
end
good.
there on decision problem. But okay, let me go into more
All right.
detail about the Turing machine. So a Turing
That's all good.
machine is an abstract concept of a computational device that. So the Turing machine. Imagine a infinitely long strip of tape, and there being a little machine at the top of this tape that could either read or write what's on the tape. So on the tape, just imagine there being like ones and zeros, and and the machine on top of this tape could either read a 1 or 0 or write a 1 or 0. And so the machine operates based on on a finite set of states, with each state having associated translation rules that dictate the machine's behavior. So with this machine, an example of something that I could do is it could read a 1, and if it reads a 1, it jumps to a new address on the tape, and if it or it could like read a 0 and jump and stay where it is. So essentially what this machine's doing is it's branching. So it's so with branching, if given a condition, so there being a 1 or 0 at a certain location on the tape, it'll make a decision and do something based on that. So, and all branching really is it's or decision making. All decision making is in computing is if else statement. So if some condition is met, then I'll execute this statement. Otherwise, if that's not met, I'll do something else. And so that's what the machine's doing.
Dang.
It's really simple. I might have explained it in a really weird way. I'm pretty sure I did. I definitely could have probably explained it in a simple way. All the machine on this tape is doing is it's reading a 1 or 0, and it's making decisions based off where it is on the tape and what it's reading, and and it's either reading another value on the tape. It's based off what it read at a certain point, or it's writing. That makes sense?
Yeah, it does. So yeah, it just reads the tape. So I was gonna ask you, I think you already maybe went over this. How is the tape made before it reads it?
Oh, yeah, no, this tape is just an abstract concept. It is just a concept that Turing
Oh, okay, just right now.
devised. And he
Okay.
devised this concept to solve the halting problem. Um,
Oh yeah, you went
but
over that the halting problem,
but
right?
but the Turing machine, right? It could
Mm-hmm.
compute. Oh, I didn't even go into Turing completeness. Okay,
All right,
so
then go into it.
the Turing machine, right? This abstract concept of a Turing machine, it could do any computation. So, any computation. You could, as long as you the programmer uh, know what you're doing, you can make it do any calculation. So that's that. And so the way so to be a Turing machine, a machine has to be Turing complete. And so to satisfy Turing completeness, to be able to do any sort of calculation, um, it has to follow these three criteria. It has to be able to do conditional branching. So it must support conditional branching, where the execution of statements can change based off logical conditions. This is usually implemented through constructs like if-else statements in programming languages. So, right, I talked about branching, right? So if this condition is met, then execute some sort of statement, and if that statement is not met, then do some other sort of statement. So that's basically branching. And so another criteria which a Turing machine must meet is it must have memory. And actually, it has to have an arbitrary amount of memory, and I'll talk about that later. But basically, the system should have a way to store and manipulate data, such as variables or memory cells. So remember, I talked about the tape. So the tape would be the memory. And so the machine should have a way to be able to access and modify this data as long as needed during computation. All right. And another thing it must be able to do is it must be able to do looping. And so the system must support looping or iteration, allowing a program to repeat a series of instructions as many times as it needs. So imagine like a game. So as long as you're playing the game, you want the game to keep running, right?
Mm-hmm.
Like imagine a dinosaur game, when you don't have internet. But while you haven't died, the game's going to keep running, right? And that's looping, right? So while you keep playing the game, while you're not dead, the game logic is going to keep looping. And
Okay.
looping is pretty much just branching, because once you loop through a certain amount of statements in your loop, what's going to happen is you're going to jump to the beginning of your the top of the statement. So imagine you have a set of statements, right?
Yeah.
So you start from some sort of memory in the computer, and so you're going to iterate to the statements in your loop, right? So it's going to start from that, your starting memory location. It's going to go to the other memory location, which stores your program statements. And then after that, it's going to jump to the beginning. It's going to jump right back to that beginning memory location. It's going to repeat that if some condition is met, right? So that's branching, right? If things are good in this loop, if this condition is met in this loop, it's going to keep looping through. So with those three criteria, conditional branching, memory, and looping, you have Turing completeness, meaning you have a machine that can do any sort of computation. And I talked about arbitrary memory, right? So in the
Yeah.
concept, in the abstract concept of a Turing machine, you have an infinitely long tape, right? And so this means you have an arbitrary amount of memory, because to actually be able to do any sort of computation out there, you probably need an infinite amount of memory to do it. So like if you're doing, for example, some really super large computation of numbers. You're gonna need an infinite amount of way to store those numbers. Um, it doesn't talk about the time it needs to take. I'm sure it'll take a really long time, but that doesn't matter. As long as you have an infinite amount of memory, you could do any sort of computation given enough time, right? But
Mhm.
as you might have realized, nothing has infinite amount of memory. No computer does. Computers are considered quote unquote Turing complete, but they don't really have infinite amount of memory, hence they're not really Turing complete. But for the sake of this discussion, they are Turing complete. And an interesting thing too, even our brains aren't Turing complete. Our brains could do any sort of computation, but we don't have an infinite amount of memory. So, not even humans are Turing complete. And I suppose if there was a god that existed, the god would have Turing completeness, meaning it really did have an infinite amount of memory and could do any sort of calculation out there. Okay, that's Turing completeness. Did you get that?
Yes.
All right. And so yeah, it was invented by Alan Turing. Did I talk about Alan Turing at all? Did I?
You can go over him again because, to be honest with you, I think he went over a lot of the stuff he did, but not a lot of stuff he,
Well, I mean, yeah, he
because
wrote
I
in
know
1930s.
he's.
All this stuff I was talking about with Alan Turing, like the Turing machine, the decision problem, was written in his 1936 paper, showing that there are inherent. Yeah, so it's 1936.
All right. Oh, we're getting close to World War II.
Yeah, yeah. No, this was a lot of computer advancements were actually made during World War II. It's crazy. Like, so
Dang.
many inventions during World War II.
Did Hitler do anything?
I mean, yeah, Nazis did make a lot of inventions too.
No, but with computer.
Yeah, I'll talk about that too.
Whoa. All right.
Well, not
I'm
Hitler
excited.
himself. I don't think Hitler was
Dang.
smart.
For real? I mean, he
Dude,
was a vegan, so.
he was a drug addict, and I think his brain was mushed, dude. I mean, obviously his brain was fucking mushed because he did just insane shit.
I know. Like,
But
geez.
the German people, I think, were just there was a lot of like universities in Germany and stuff at the time. So I think they made so many inventions because Germany before World War II had a lot of like intellectual might. Albert Einstein was born there and raised there. A lot of other scientists, a lot of other influential scientists. So
Yeah.
yeah, so Hitler, just took that. Well, I mean, he also made some dumb decisions. Okay, this is kind of beyond the topic of the video, but
Yeah, let's continue with the stuff done during World War II and also with Alan Turing.
yeah, all right. All right. So Alan Turing's work in World War II. So we have, so um, he was hired by, so he was British, and he was hired by the
Hmm.
British military to do code breaking with the Enigma code. So talked about the Caesar cipher, and during World War II, the Germans had an Enigma cipher. So they had a machine which had a unbreakable code at the time. It and so Turing and his team, at the time, they just had to like um, they had to do other indirect ways of trying to break the codes. They didn't actually have like a actual way of breaking the encryption yet, and they um, so they usually couldn't, and so it was until the invention of the bomb machine when they were able to actually break Enigma messages that they could figure out what the Germans were saying. Um,
Well,
yeah, that's pretty much all I have on that. I don't know like all
yeah,
the
I
ins and
mean,
outs of like the Enigma machine and like how they broke it. I used to know, but I forgot.
Oh, that's
What?
fine. All right. So,
Yeah.
are we still? Is there more stuff in World War II, or with this other guy, Alan Turing?
I mean, I did write some other notes on him, but uh, I mean, yeah, he basically invented a very core concept for computing. Um, and he did do some other work with computing later on, but ended up killing himself.
Oh my.
So he died at
Do we
like
know
what,
why?
46? So like it was found out he was gay pretty much, and the British government was like, since it was like outlawed at the time being gay, it's illegal. He was given the choice of either going to jail or taking hormones to suppress, his gay horniness. So he chose the latter, and the hormones he had to take, they altered his like personality and stuff, and I guess he became depressed because of that. And yeah, so fortunately, yeah, killed himself.
Fortunately.
Unfortunately,
I'm kidding.
yeah.
Um,
Oh,
that
and
sucks.
also another thing he did is he proposed something called the Turing test. Um, so this test is a benchmark for determining a machine's ability to exhibit human-like intelligence. So here's already thinking about AI at the time too.
Oh my
So
gosh.
he devised a test to test whether a machine was truly intelligent. So
What
this
was the
test
test?
involves a human evaluator interacting with machine and a human, not knowing which is which, right?
Yeah.
So if the evaluator cannot reliably distinguish between the human and the machine is considered to have passed the Turing test. Essentially, having general artificial intelligence.
Well, that sounds like a very simple test.
Yeah, it is. I mean, the ways they devise the ways that they try to distinguish between the human and machines definitely wouldn't be simple, but yeah, that's all it really comes down to.
All
All
right.
right. So going back to World War II, the first programmable computer. So the Z3, created by a German engineer and Rod Zeus. Honestly, I don't know how to pronounce his name. I think it's Conrad Zeus. I say
Okay.
is
Well, he was a
widely
Conrad. Well, I guess he wasn't Russian, so.
yeah. So yeah, so his Z3 machine is widely considered to be the world's first fully functional digital and programmable computer. He didn't actually have any. I don't think he knew about the Turing concept. I think he was just kind of lone wolfing it, just going off his own with it. But it was a pioneering achievement in the history of computing. So, Conrad Zeus began working on the Z3 in the 1930s, and he completed it in 1941, Berlin, Germany. So yeah, this is before the concept of the Turing machine. So he definitely didn't know about that. So the Z3 was fully electrical mechanical computer, which means it used both electrical and mechanical components for calculation. So yeah, at this time, the way logic flow in a computer worked. So nowadays we have transistors, which are fully electrical, but back then the transistors, quote unquote, were both electrical and mechanical. So like um, so to direct the flow of logic to redirect the flow of logic, there would probably be like a little lever that had to move to for the flow of logic to go somewhere else. So this physical movement definitely made it a lot slower than today. So the architecture, the Z3 used telephone switching technology, and more than 2,000 electrical mechanical relays for its operation. So yeah, it operated on relays, which was basically the transistors at the time. And it used binary logic, ones and zeros. And so the Z3 was programmable using punched film strips, which served as the form of machine code. These strips contained
That sounds a
instructions.
lot like the. That sounds a lot like what you were talking about with the hole punched one. I mean, is this like the execution of that theory? Because you said it was a theory before, right? You know what I'm talking about? With the it would
No,
read the tape.
I don't think it's the same because well, it is kind of the
Okay.
same the way it's read and stuff. But the thing is with the census tabulator, um, there was no like machine instructions. It was just, oh, is this person married or whatnot? And then it's just gonna add up. It's just gonna use that information to add to other information, like, oh, this is how much people were married based off this amount of hole punches. But these scripts fed into the computer with the hole punches in it, they included instructions for the computer. So things like um, add this or
Turn
move to this.
on.
No, not really. That's not a machine code
Okay. I
for
was
any
just joking.
machine. It might be a machine code. I don't know. I haven't taken the architecture class at CUC yet, so I mean, I'll be a lot more knowledgeable on this stuff after I take that. But
All right.
um, yeah, this machine code just gave instructions to the computer, and but the thing is, so we talked about Turing completeness. Apparently, ignoring infinite amount of memory, because obviously nothing can have an infinite amount of memory, but ignoring that, it apparently wasn't Turing complete. So, and the reason why it wasn't is because it couldn't do branching. So its flow of logic couldn't be redirected based on certain conditions. So the programmer basically just had to tell it to like do certain calculations. Couldn't do any more fancy business with it, like, oh, if I don't know, can't really think of an example on my top of my head. Like if
Oh, that's
this
fine.
number is even or something, then make the number odd. It couldn't do stuff like that, and it was just used for speeding up scientific and engineering calculations for the Nazis. That's all it was really used for. So it was basically just a calculator. Yeah, it's basically just a calculator. You could make it do certain formulas, stuff like that. That's all it really was. And so yeah, after he finished it, it was bombed during the Berlin bombings. So yeah, that's that.
Rip. And that was the first computer, right?
Oh, well,
Well, not the
yeah.
first one, but it was very specific. Like,
Well, I mean, let's define computer as a machine that has Turing completeness. Since it didn't really have Turing completeness, ignoring infinite amount of memory, then it wasn't the first computer.
okay, then what was it then? What was so special about this
It was the
um
first
device?
programmable computer.
Okay.
Yeah.
All
Or
right then.
first programmable machine, I guess you could say, since we're sticking that definition of computer.
Yeah. So, um, do we have more stuff during World War II, or are we getting into the Cold War?
Oh man, how long has this been going on? It's already like 10:40, 10:47. Dang.
It's gonna yeah, we start around 9:33, but let's just to be focused, and we'll get through this. You know what I'm saying?
Yeah, yeah, I want to
So
definitely finish this since, I put a lot of time into this.
it's all good. What's
Yeah.
the next thing?
Von
I think you
Neumann
said something about
architecture.
ooh, the architecture. So what's so special about this guy's architecture?
So von Neumann architecture is a fundamental design concept for modern computers. So all computers today are based off von Neumann architecture. And so it was proposed by Hungarian American mathematician and computer scientist John von Neumann in the mid 1940s. So still in World War II, and has since become a foundation for virtually all general purpose machines, general purpose computers. The von Neumann architecture is characterized by several key features. Stored memory concept. So in the von Neumann architecture, both program instructions and data are stored in the same memory. And apparently this was a pretty influential concept at the time. Program instructions and data being stored in the same memory. Okay, and this concept allows for the computer to be programmed with a series of instructions that can be fetched, decoded, and executed by the central processing unit, or CPU. And so it also had a CPU, the brain of the computer,
Yeah,
and
that's
it
what
is
people.
responsible. Um,
I mean, yeah, a lot of
so,
people spend like half their budget if they're buying a computer on the CPU. So it must be. So you're saying this was one of the first. This was the first computer with a CPU, or
no,
something like a CPU?
it's just the concept of the architecture.
Oh,
So
okay.
so I mean, all a computer really is doing is so it has a CPU and it has the memory, right, or the RAM. And
Yeah.
the CPU is really not all that complicated. All the CPU is doing, so it has a section for doing calculations, and so the calculations are for like addition and subtraction. With addition and subtraction, you can do all other types of calculations. So that's all the all the ALU and the computer is really doing is just doing addition, subtraction. I think some other things too for logic and stuff. So the ALU part of the CPU does, the calculations, and then also has a control unit for. I think the control unit is for moving instructions around in memory. So that's all the CPU is really doing. It's just doing calculations. It's just moving things around in memory. I might be wrong on that. I
No,
hope
that's
I'm
a
not.
pretty accurate.
So yeah, the control unit manages the flow of instructions. Oh yeah, I did write notes on it. So the control unit manages the flow of instructions and data within the CPU and coordinates the execution of the program. Right. So the CPU is interacting with the memory on the computer. Right. So the program is being stored on the memory of the computer or the RAM, and the CPU is fiddling around with that memory.
Hmm.
So yeah, that's all a computer really is.
Yeah, nowadays I would say that's what a computer is. I mean, there's also I mean, I guess back then they weren't even thinking about like storage and stuff like that or graphics cards.
I mean, they definitely weren't thinking about graphics cards. They
Oh
definitely
yeah,
weren't.
they weren't even thinking about graphics cards until like the 60s, I'd say, because they need
I
to
think
like actually see stuff on their computer in the 60s
well,
because they didn't have monitors back then.
here, no, that's a graphics card is really just a CPU actually. It's um it's really just a CPU, but it's just it handles certain types of calculations better. That's really all a GPU is.
So you're saying a GPU does not deal with graphics?
I mean, a CPU could deal with graphics just fine. It's just graphics requires a lot of calculations and stuff, so GPUs are built to handle those calculations better. But a CPU could do just fine. A
Okay, it can
GPU
do
is
just
built off,
it can do the okay.
yeah. So all um um all integrated circuits, so like CPUs, GPUs, and yada yada yada. There's different forms. All of them are built off von Neumann architecture, right? So a GPU it has the same architecture as a CPU. It just I wouldn't really say the same architecture, but it's they're doing the same stuff basically. That makes sense.
Okay. Yeah, I mean it does make sense because it can do the same thing, but um the CPU is going to be doing stuff while the GPU is doing other calculations. So it's kind of like, like a just separating the tasks,
Yeah,
you
yeah,
would
yeah,
say.
yeah. That concept is
Okay.
called parallelism in computers. So
Oh,
nowadays our
oh, whoa.
computers have like I think my computer has like 8 cores, so it could do like 8 different tasks at once because essentially has 8 different CPUs or 8 different integrated circuits in the CPU to multitask things.
That makes sense.
Right? Yeah. All right. So that's von Neumann architecture. let's move on to integrated circuits. So I was talking about integrated circuits earlier, but at this point they weren't invented yet. So before integrated circuits, computers handled logic with vacuum tubes. I think the vacuum tube era was like in the 50s, where the flow of logic computers was handled by vacuum tubes. And before that, I talked about the flow of logic being electromechanical with like relays and stuff. And so, okay, so actually the transistor was apparently invented in 1947. So, so the history, so integrated circuits are built of transistors, and all a transistor does is either block or allow the flow of a current. And this is how you build logic gates. And so with logic gates, then you build, the CPU, basically. Let's talk about the history of it. So, transistor invention. Right. So I kind of was jumbling around there. I kind of I don't think I really organized my notes well enough for like for transistors. But
Oh, that's fine. I mean, I know that's something that's very important to a computer, right? Transistors.
yeah. So like before, to make the logic gates, like at first you had for electrical computers, the first thing they did to make logic gates was the relays, right? And I talked about the first programmable computer using relays. And then, since the relays they actually move a bit, and it wasn't moving at the speed of light. It was actually had to do mechanical movements. It was really slow, and so then they invented vacuum tubes to make logic gates. And so vacuum tubes were fully electrical, so it could do calculations a lot faster. And so those also had its downsides. So then transistors were invented, which fully electrical and didn't use vacuum tube technology, basically. Um, so the history of the ICs begins. Oh, okay, I wrote some things wrong. Whoops. Okay, so I didn't really include when transistors were invented.
Oh, that's fine.
And I hope I didn't make a lot of
But I
errors
mean,
so far.
no, it's all good. Just, I mean, so you talked about transistors, right? Just now, or do
Yeah.
you have more stuff to talk about transistors?
Not really. I should have put
All
more
right then.
stuff there. Yeah, sorry about that.
It's
I
all
mean,
good.
I really only had a day to put all this down. So,
Dude, it's all good. We do we have other stuff though to talk about?
for transistors, yeah, I have one more thing. Moore's law. We can't move on from transistors without talking about Moore's law. So, Moore's law is an observation and prediction made by Gordon Moore, co-founder of Intel Corporation, in a 1965 paper titled "Cramming More Components onto Integrated Circuits." Moore's law states that the number of transistors or components that can be integrated onto a semiconductor chip of a given size doubles approximately every 2 years, leading to a significant increase of computational power while reducing the cost of electronic devices. So essentially, what he's saying is he predicted that every 2 years, the amount of transistors that can be fit into a CPU or integrated circuits is going to double. Right, so in the same size, there's going to be twice as much computing power every 2 years, and it turns out his little prediction of what's going to happen was pretty accurate. And so nowadays we're actually reaching the physical limit of how much transistors we could fit onto a integrated circuit. So we might be
Crazy.
we might be close to the end of how fast classical digital computers can go. I'm gonna talk later about
But they're already
how
pretty fast, right?
yeah, but I'll talk later about ways that they're trying to find around it, or ways they actually did find around it. But essentially, it's gonna have there's gonna be a point where digital computers are gonna reach its limit of computing power for a given size. Oh, and I didn't even talk about the first general purpose computer yet.
Yeah, and that was like in the 40s, right? The
It
ENIAC
was in
or EMIAC?
it was probably in the 1940s. Honestly, I was running into some conflicting information about like the first actually Turing complete computer. I wrote
Oh,
about
why
the
is that?
UNIVAC one, but I
Yeah.
think there might have been an earlier computer that had Turing completeness. So I'm unfortunately I might have gotten that wrong. I might get this wrong about the first general purpose computer, but I'm going to talk to the UNIVAC. So the first general purpose computer, quote unquote, is often attributed to the UNIVAC 1, which is designed by J. Perspill. I can't pronounce the name. I'm not even going to attempt something. In the early 1950s, the UNIVAC 1 was the first commercially produced computer designed for general purpose computing tasks, hence making it Turing complete.
All right.
All right. I'll just skip over that. The rest of what I have for it because we gotta get through all this. It's already 11.
All
All
right,
right.
we got this though. Come on.
All right, let's talk about programming languages. So at first we just had machine code, right? Just zeros and ones, and these represented just operating system calls, or not operating system calls. These representing CPU instructions. So you had to talk directly with the CPU, the program.
Yeah, and when was
Um,
this?
like before the uh, like sure with the first programmable computer, so like the 1940s.
Well, okay. All right, keep going.
Okay, so machine, yeah, assembly, so machine code, and then the so as you can imagine, typing in ones and zeros on punch cards is pretty fucking tedious, and it was.
Yeah.
So they had to, so the first higher level programming language was known as assembly language. And this is pretty much machine code. Like it's still you still had to talk directly with the hardware, but you did so with symbolic representations of machine code. So you actually had some English in there, like um, move, read, write, adding stuff like that. But they were still based off machine uh, machine code. So it was still very tedious. You're still talking directly with the hardware. And so yeah, but that was the first ever higher level programming language. And then okay, let's talk about Grace Hopper. And she
Ooh.
invented the first compiler for um for a higher level programming language where you didn't have to talk directly with the machine code. So during the World War II, Grace Hopper joined the United States Navy Reserve, and in 1943 was commissioned as lieutenant. So yeah, she sounds like a badass. She was also pretty
But
smart
as good
because
as Ada though?
maybe. So she worked on the Harvard Mark I computer at Harvard University, where she became one of the first programmers of the early electrical mechanical computer. So programming and COBOL. So COBOL is considered to be the first high-level programming language. And so she devised a compiler to compile this higher-level programming language into machine code. Okay, so a compiler, so high-level programming languages don't have to be concerned with they're more human readable basically. So with assembly, you had to know like the computer architecture, like the CPU instructions and whatnot. But with a high level programming language, you don't have to be concerned with that. You could worry about bigger things. So like with assembly, you had to move through. You had to do certain CPU instructions and dealing with the memory directly to like add a number. But with high level programming language, all you have to do is type a statement like, A plus B, And so the compiler takes that statement and it converts it down to machine code so that the computer can understand. Right? Because a computer can only understand machine code. All right, COBOL stands for Common Business Oriented Language. And so it was designed for business data processing. And so have you heard of the term debugging?
Yeah, I did. Like, there's bugs in the computer, like viruses, hacks, that kind of thing.
No. So a bug would be like when the program doesn't work as you intended.
Oh,
And
okay.
so when she was working on the on the Harvard Mark One, she was not getting some output that she wanted, right? And so she looked through the computer, right, because it was really bugging her, because she couldn't figure it out. So she had to
Hey,
look. She had to look into the computer, and it turns out there was a moth inside the computer messing with the electricing, right? And
those
so
dang
that's how
moths.
so that's how the term debugging got termed because of a fucking
They could have
bug.
just called it demothing. Yo.
Yeah, but I mean, doesn't make sense because bugs bug you.
Okay, good point. Good point.
Okay, so
All
COBOL,
right.
COBOL invented in 1959, the first high-level programming language, right? All right,
Mhm.
so I'm skipping some other programming languages because I don't think they're important. So let's go to C. So C, which just stands for compiler, was invented in 1962, developed by Dennis Ritchie at Bell Labs, and it became the most influential programming language because it was known for its efficiency and portability. Okay, so C code is machine dependent, meaning it could run on any computer architecture as long as the computer could run C code. Right? So, okay, so with assembly, right, you had to be worried about the computer's architecture to be able to run the code, right? So so some code that could run on one computer might be completely different on another computer because of its differing architecture. But with C code, as long as both computers could run C code, they could both run the same C code. So as long as it had a C compiler, so as long as both computers had a C compiler, they could both run the same C code.
Mhm.
All right. And then C++ was invented in the 1980s. It was an extension of C, but this time it introduced object-oriented programming. I'm gonna skip over that because I don't think it's too important. I mean, it is important, but like, you know, but we're just gonna skip over that object-oriented programming. Okay, and then Java. Also I could probably skip over Java too, but it's like the last section on modern times that I have. So okay, I'll just talk about Java. Okay, so Java invented in the 1990s.
Oh, Java. That's
What
kind
runs
the thing
Minecraft?
that runs Minecraft. Yes. So you're saying this is very important when it comes to, computing? Like after
Um,
those 3 decades from the 1960s
well,
to
it
the
had a
1990s when Java was invented?
it had a very important aspect to it, but it wasn't the first programming language to have this aspect. But I just want to talk about Java because
All right.
the other so so Java is the first interpreted. No, it's not the first interpreted language. I don't know why I put that there. But oh no. Okay, so it's one of the first interpreted language that uses a virtual machine. Okay, so with C, right? It's machine dependent. So as long as two computers with different architectures could compile C code, it could run the same C code, but it wasn't operating system independent. So C, had libraries that had operating system calls that were specific to that operating system that I was running on. So both the computers, different architecture, had to have the same operating system. But with Java, it ran on a virtual machine on both those platforms. All right. So when I'm saying platform, I mean the operating system and the architecture. So the both computers had so Java. As long as you had Java installed on both those computers, the same Java code could run on both platforms, right? And the way it did this is it had a virtual machine on both the JVM, the Java virtual machine. So when you install Java, what you're doing is you're installing the JVM, right? And so this Java virtual machine makes it so Java code is ran virtually on your computer. So think of it like a computer inside a computer. So this this virtual computer is virtually running on the hardware. It acts like a computer, but it's virtually running on the computer. And so Java is ran on that virtual machine. That makes sense?
Yes.
Yeah, and so this is important for web browsers because when you're running a website, it has to be platform independent, right? And you don't want the website running on your hardware of your computer, because if that were to happen, then you could get viruses pretty easily, right? So it needs to be ran virtually on your computer. Hope I didn't get that wrong. But
No, that's all good.
yeah, so that's all I have for modern times.
Dang.
Yeah.
But I mean, a lot of other stuff happened in modern times, right? I mean, let's be
Yeah.
real here. We're still in the 1990s.
Yeah, you're right. Oh, I mean, a lot of stuff did happen, like the internet and stuff, but I didn't have a lot of
It's all
time to
good.
put everything down. We've already been talking for like an hour too, so I think I did put a
Yeah.
lot
All
down.
right, then that's all good. I mean, a lot of people know what happened past the 1990s if we think about it, like most people that watch this podcast were probably born in the last few decades. So I'd say that you know already, but I mean, I'm hoping that you guys know about more stuff about computers that a lot of people probably don't even think about. People probably don't even think about all this stuff that happened past before computers were first in the house. You know what I'm saying? Like, yeah, you're probably thinking, oh, I'm thinking about the computer I'm using right now. I'm thinking about when did that first start happening? But you didn't think about all these machines that happened before it. So
Yeah,
huh,
I think it would be
all right.
pretty pointless to include like, oh, the history of like the GPUs that run your video games, for example.
Exactly. All right then. Let's go on to the last topic then. So, the last topic is beyond. So, the
Yes.
future basically. What's beyond this time, Kyle? Like what's your actually I guess I'll go into my idea of what I think a lot of things will be virtual in the future, like people will be able to do stuff in the air, stuff like that, wear glasses maybe, do some stuff. We're getting it more into that virtual realm, but rather slowly, kind of like how we're probably going to all start drinking Coke or Pepsi Zero in the next 30 years. And we're not going to even drink regular Coke, even if regular Coke is better, in my opinion, or regular Pepsi. It's just a lot easier for everyone to drink one thing, but to slowly ease our way into it because, a lot of people uh, like drinking it now, because of health reasons, but people are
Uh,
gonna
sorry,
do it more just because of what's up.
I got like 5% of that. Are you talking about like virtually drinking a Coke?
Oh no, I'm just talking about the like an example. So an example of like us slowly switching into the virtual world is kind of like how Coke or Pepsi is slowly trying to urge us to drink more Coke or Pepsi Zero because that's kind of a new product they're selling, and they can't really just go from that to that because that's what happened with New Coke. When they started selling New Coke, no one was buying New Coke. They're just wanting the original. So they're slowly trying to get us into it. They're trying to wean us onto it, but
Oh
you
yeah, I
never
mean, I
know.
kind of think that's stupid Diet Coke and whatnot. Because apparently like sugar is more fattening than like Diet Coke.
Oh, so you think drinking Diet Coke is better than drinking regular
Oh
Coke?
wait, I'm stupid. Yeah. Okay, wait. Okay, I don't really know what I was thinking, but
No, it's all good, man.
what?
But I'm
But
gonna just finish my. Oh yeah.
oh yeah, I know. I actually did add some notes for like the future of computing.
All right. Well, I was just gonna go over my stuff first, and then you can do it. Just because I know you'll probably just go over it real quick. I feel like iPhones are definitely gonna get more on or even in Ayo pause, because we're already getting the Apple Watch and everything. People are not even using their phone anymore; they're just walking around with their Apple Watch
Are you talking
and
about like
being like,
Neuralink?
"Yeah, that Neuralink is gonna be like the future." I'd say. Uh, and yeah, I to be honest, when it comes to the future, I just see everything just going faster. I don't see too many changes because so far, not a lot of stuff has changed, like you said, since the 20th century, because it's just gotten faster. We've just been following these concepts that we've
Yeah.
learned and developed in the 20th century. So
Yeah,
who
even with
knows?
AI too, like the concept of Neuralinks. I mean, AI, the development of AI has really been going on since actually the 1940s.
That's
But
crazy.
the reason why we couldn't we didn't have fucking ChatGPT back in 1950s is because we didn't have enough computer power.
That makes sense.
Um, there's definitely been more like advancements like with AI algorithms and stuff. Like really AI like concepts for AI have really been starting like in the 1950s. So a lot of our core computing aspects that really started like like back then, really, and it's
Yeah.
just been getting
Um.
faster, more
Okay, so
powerful.
you had some notes of the future. So what would you say is the future of computing, Kyle? Would you say that we're stuck in this digital age, or you think we're gonna find something else? So I know you're
Um,
talking to me about a different line of computing being
yeah.
in the future.
So I talked about Moore's law in modern times. So like yeah, we're approaching the limit for how much stuff we could
Transistors.
pack. Yeah, how much stuff we could pack into a limited size in a CPU. And so one of the ways to get around this is quantum computing. So quantum computers use the properties of quantum physics, which are just weird. It just
Okay.
goes beyond our natural intuition. I'm not
Could
an
you
expert on it,
maybe
so I'm
simplify it down a little bit though
yeah.
to a
Well, I mean,
physical sense?
the thing is, um,
It's theoretical.
no, the thing is, I'm probably gonna sound really stupid explaining all of this.
All
Um,
right.
'Cause I'm not a
Quantum physics major.
yeah. Well, I mean, I took physics in high school, but I dropped out of it second semester. Uh,
All right. Well,
so
okay. So after the quantum computing, what other stuff are you going to talk about?
I'll talk about quantum computing. So yeah, so
Okay.
it's overcome the limitation of Moore's law. It could overcome the more limitation of Moore's law. So okay, so let's talk about the two aspects of a quantum computer: superposition and entanglement. So in classical computing, a bit can be in one of two states, one and zero, right? In
Hmm.
contrast, a qubit in a quantum computer, their most basic form of information, exists in a superposition of both one and zero states simultaneously. And if that sounds like magic, it basically is. I don't really know what else to say. It's basically magic. So this means that
That's
for a
fine.
quantum computer with n bits, it could represent and process 2 to the n possible combinations of zeros and ones simultaneously. So this is exponentially speeds up algorithms. So for a classical computer, right? So the more bits you have on a classical computer, the speed of the computer rises linearly. But with a quantum computer, because its qubits are magically 1 and 0 at the same time, or can be, its speed goes up exponentially of more qubits. I've wrote more, but I feel like I could stop there. Basically,
So that's
magical
yeah.
fucking magical computers is what they are.
Magical computers is going to be the future.
Pretty
Dang. Any
much.
other stuff like? Dang. What are people's PC setups going to look like? Gaming setups going to look like in the future?
Oh well, I mean, it has drawbacks. So right now, like
Dang.
they're not that precise. Like the because you know when we measure the qubits in a computer, they could have like unexpected results a lot.
Oh, so they're
Um,
unpredictable.
yeah, they're yeah, exactly. So I mean, they're working on making them more predictable, but yeah, right now they're pretty unpredictable. And you have to freeze them to like near absolute zero to make them run, because the more heat, the more unpredictable it gets.
Oh, okay. So you
So
have to make it cold.
yeah.
So there's a lot
Apparently,
of fans, I'm guessing.
yeah. What a coolant. I mean, in reality, they put it in like a special refrigerator. But actually, apparently, they found a way to not have it be at absolute zero and still be accurate. So there's definitely going to be probably more, ways to make it more commercially viable. But right now, it's not.
That makes sense. All right. You have
Yeah.
anything else you'd like to say about computing, the history of computing, like what it all means? Like, to wrap it up, what would you say is like you'd like to say about it? Why you think it's so important?
Why computing's so important?
Yeah.
I
To you.
mean, me, I just think
Yeah,
it's
to you.
really interesting. I mean, I've been interested in computers since I was a little kid. I remember like smashing open remotes and stuff to see what was going on inside when I was like a toddler. Uh, yeah.
Yes, I can imagine baby Kyle smashing remotes and pissing off the parents because they're
Yep.
just trying to watch the Breaking Bad, and you're trying to break some bad with those remotes.
Oh yeah.
All right. Okay then. We can end it there. So Kyle, did you want to shout anything out? Any social medias or any projects you're doing right now?
Nope. Um.
Dang, not even on OnlyFans or anything?
Nope.
Dang.
Sorry about that, John. Yeah. No, you
Okay.
want to look at my OnlyFans? Huh?
Let's end this. Okay, so let me know how you feel about this person in the comments below. Let me know if you'd
Well,
like to hear from Kyle again. What's up?
I mean, I really hope there is no comments on the video.
Well, just let me know how you feel about Kyle, and let me know if you'd like to hear from him again. I sure do.
I mean,
Thanks
this
for
is the
listening
first
to.
time I'm going on YouTube, so yeah, it's pretty nerve-wracking. Even if
I know.
even if there's only like 20 people looking at the video, it's still pretty nerve-wracking for me.
Well,
But
it's gonna happen. Thanks
yep.
for listening to this week's podcast, and you will see me next week talking to somebody else about something else. So yeah, hopefully you learned a lot about the history of computing from my boy Kyle over here, and yeah, just hope I see you next week, and you know, hear the podcast next week. I don't even know what I'm saying. So I'll see you guys next week, and have a good time listening to the next episode and this episode. All right. Bye.